All right, good morning, gentlemen. So today the plan is that we're going to go over the metric system factor conversion, which this should be a lot of review for you, especially because you learn this in integrated science. However, I am going to be reviewing it. We're going to do a couple examples, and then for your homework, you'll be having a graphing worksheet and a metric conversion practice worksheet. I did post on Canvas the basic skills key for you to look over. That is an ungraded assignment. However, I just wanted you to practice those skills and recall a lot of the information. And if you struggled with it, then please reach out to me so we can email or we can Zoom or meet in person to help you really understand those, because those skills are what you're going to need to succeed specifically in chemistry. So, to get going, as a reminder, repetition is your best friend. So, especially with metric conversions, if you don't feel very strong in that area, it's very important that you practice, because you can't really understand metric conversions until you really practice. And while there are multiple ways to do them, practicing the method that works best for you is really going to help you succeed, because you're going to be needing the skills of converting a lot more, and it's only going to get harder from here. So, an example right now is, what is 36 grams in milligrams? So there's two ways that you could find the answer. One way is by sliding the decimal over, and so I know I have, I have 36 grams. And in grams, if I want to go to milligrams, I know that there are 1,000 milligrams in 1 gram. Goodness. There are 3 zeros in 1,000, and so all I'd have to do is pretend there's like a decimal place there, there's always a decimal place there, and move it over like I have, I'm going to do this, like I have right here. So I would slide over my decimal, and then I would plop it there to get 36,000. Another way to do this is the factor conversion method with train tracks, where you'll cross cancel the units right here. So like here's my grams, I cross cancel my grams, I multiply across, divide by anything on the bottom. Regardless, I should end up with the answer of 36,000 milligrams. So whichever way works best for you is fine. However, as long as you understand how to get where. So as an as a review, the metric system base units, these are the ones that we use in science. And so when we're measuring mass, we're always going to do grams. When we measure volume, it's always in liters, temperatures in degrees Celsius, length is in meters, and time is in seconds. I recommend writing this down somewhere so you have it as a reference. So I would strongly suggest pausing this video, writing this table down, and then when you're done, to continue hitting play, because this is extremely important information and a good reminder for you to know the base units. Now, if you decide that you would like to do the sliding method, or even not the sliding method, really good way for you to note in your head with factor conversions is our stairs right here. We have a kilo, hecto, deca, unit was in the middle, where that's like our 0, our deci, centi, and milli. So a good way to know is that King Henry doesn't usually drink chocolate milk. So the King Henry doesn't is our positive. We're shifting to the left. Yeah, we're shifting to the left. And then with our drink chocolate milk, drink chocolate milk, we're shifting to the right. So we're getting smaller to the right, and then to the left, we're getting bigger. I hope you understand. So this is my left. This is my right. I write with my right hand. I don't know the directions that you're going to see this. So anyways, this is also something really important to write down, because it's a really good unit to know. So like a deci is a 10. And so if I'm going from grams to decigrams, I'm only going to multiply by 10. Yeah. Whereas if I'm shifting to the left, if I want to know grams to decagrams, I'm going to divide by 10, because I have a really big number and I'm making it into a smaller number. Whereas if I have I have a small number and I want to make it into a smaller number, it's going to look bigger. All right. So a factor conversion is a fraction that you use to change the units of a number. Doesn't change the value, it's just how the value is described. And so the only thing you're really changing in this is the units. That's it, because I can go from grams to kilograms, I can go from grams to milligrams, I can go from kilograms to milligrams, a bunch of steps like that. However, the value of my number is going to stay the same. So what I mean by that is if I have, you can see, I have 10 grams. If I wanted that in milligrams, I'd be adding 3 decimals because it would be a lot because I'm making the number smaller. So I would have 10,000 milligrams. However, if I had 10 grams and I wanted it in kilograms, I would be moving it over to get a very, that's kilograms, a very small number. So the reason I knew how to do this over is there's 1 kilogram and 1,000 grams, and so I would just take my decimal and go 1, 2, 3, and that gives me my kilograms. However, if I start with my 10 grams and I want to go to kilograms, I'll have my 0.010 kilograms, and that is actually equal to my 10,000 milligrams, which it doesn't feel like it. However, just because the unit's different doesn't mean that the value's different, because I can go from here and say, okay, if I wanted it in grams and I wanted this in grams, it would be equal to 10 grams. When you're doing a factor conversion, your steps are to write down the starting number with units. And so, example, I had 10 grams and I want to make it kilograms. I write down my starting number, my unit. Determine your conversion factor. If I want grams to kilograms, then I will set it up so my units will cancel diagonally. So you can use the train track, which I'm going to use the train track. It helps me. If you work better by doing fractions, that's fine. So I have 10 grams, and I know in kilograms, because that's what I want to end up with, I put my kilogram here, and I want to cancel my grams out. And the only way to cancel is diagonally. So I know I have to put my gram unit here and my kilogram unit here. In kilograms, in 1 kilogram, there are 1,000 grams. And so now I will multiply across, and then I will divide. So when I divide, I get 0.01 kilograms. Yeah. So determining a factor conversion. So if I go from millimeters to meters, there's a difference in 3 decimal swoops. Therefore, there are 3 zeros in my conversion factor. And so a good way to know when you're determining is to learn to think of each conversion factor using for every speech. So like I said, for every 1 meter, there are 1,000 milliliters, or for every 1 kilogram, there are 1,000 grams. And so my conversion will look something like this. However, I can say this phrase for anything. So, for example, for every gram, there are 1,000 milligrams, or for every kilogram, there's 1,000 grams. For every centigram, for every gram, there's 100 centigrams. It's just really getting that phrase in to help you understand what conversion you're using. So there's an example right here. There are 456 grams of copper on the balance. How many kilograms is this? I'm so upset. I wanted to cover this, but that obviously did not happen. So first off, there are 456 grams of copper in the balance. How many kilograms? I'm given 456 grams, and I asked for how many kilograms would that be. And so I set it up. I set up my 456 grams of copper, and I know there's one in every kilogram is 1,000 grams. I want to cancel my units out, so I'm going to cross cancel. So I'm able to cross cancel these out when I divide. And then I'm going to multiply my 456. So my first step is I'll take my 456 and I'll multiply that by 1, and I get 456. And then I divide by 1,000 to get 0.456 kilograms. So for every 1,000 grams, there's 1 kilogram. So now I have a couple following for you to try. I'm also going to do them with you. So I will work on them. So individually, I would pause this video and work on them, and then we will discuss the answers momentarily. All right. So the first one is 2.4 kilometers is equal to how many meters? So I know that in 1 kilometer there are 1,000 meters, and so all I have to do is take that number and I multiply, because I would cancel out my kilometers. So I should get 2,400 meters. So 2,400. 0.56 grams is equal to how many milligrams? I know in every gram is 1,000 milligrams, and so I also will multiply that by 1,000, and I'll move my decimal place over so I can get 560 milligrams. And my final one is 9,000 milliliters is equal to how many liters? And every liter is 1,000 milliliters, and so I divide by 1,000 to make 9 liters. There are the answers. Make sure that you are always putting units down on your numbers. I do not want naked numbers. So, metric systems are extremely important that you don't mess up and you know what you're doing. So here's an example, is that there was a time, and this was in 2014, where NASA lost a Mars orbiter because of the metric system mix-up, where they didn't convert a unit correctly, and so they were kind of in trouble, and they lost that orbiter, which orbiters are very expensive, as you know, and so having this small error actually jeopardized this entire mission, because they lost the orbiter, because the orbiter wasn't close enough to the planet to get in its gravity, and so when it got a hold of it, it kind of ricocheted off, and we lost it. Did not get it around Mars like we planned. So that's why it's really important that you know how to do these conversions, but you know how to do them correctly, because, you know, in the future you could be an astrophysicist and you're at NASA and you accidentally do a conversion wrong, and you could lose a very expensive piece of scientific equipment that is millions of dollars. So know how to do your factor conversions. All right, moving on, we're going to talk about our measurements in science. So there's 3 kinds of numbers in science. Number 1 are the numbers obtained from definitions or constants. And so an example of that would be the speed of light, the force of gravity. These are numbers that are given to you, and there's something that's been tested and proven on multiple occasions, and so it makes them a constant. It's a number that will always be the same, no matter what. And these numbers, they don't have any uncertainty in them. We can 100% say these have been tested. We know these for a fact. this is the number. So for speed of light, it is always, always, always 3 times 10 to the 8th meters per second. And for force of gravity, it's always 9.8 meters per second squared. We know that for a fact. So there's no uncertainty in those numbers. Number 2 is numbers obtained from a small count. These small count can be I have 14 paper clips, or there's 4 presidents' faces on Mount Rushmore, or Mrs. McCaslin has 50 houseplants. These numbers have no uncertainty either because you're counting them. So you can say, no one can come and tell me there's 5 faces on Mount Rushmore for the presidents. I know that there's only 4 because I can count them. They're easy enough to count. The third number is obtained when we're using a measuring device or when we count something that's very, very large. And so what I mean by that is I'm measuring the length with a meter stick. The length that I'm measuring, I can make an estimated value. Or if I'm measuring volume of water, or if I'm estimating how many Jolly Ranchers are in a jar. These numbers have estimated digits because they're uncertain. And what I mean by that is if you recall in physical science, when you measure with a measuring stick or a graduated cylinder, you can always go past the smallest point and make a decimal because you can measure in between those lines. You can make an estimate about the value that you're measuring. And so it's important to note that these ones have uncertainty because I can say it's one way, but someone else can say, hey, I think it's this way instead. And so I can't for 100% say, you could say, hey, there's 50 Jolly Ranchers in this jar, but I could say, no, I think there's like 60. So I can kind of estimate and give my uncertainty, or someone else give me their uncertainty with their value. So uncertainty is like, what is it? How do we decide? How many decimal places do we include? How do we know what numbers are certain when we are measuring? And so a good way to note is that no matter what, we're always going to have an estimated digit when working with uncertainty. And what I mean is when you're in the lab, the final number that is done is always your estimated value. This is what introduces our uncertainty because we don't always agree on the reading. I've already kind of talked about this. So for example, when you're measuring in the lab specifically, you determine what the line represents. And so for example, if I have a graduated cylinder, for example, I'm just going up to 20. These lines represent 1 for me. However, while these lines represent 1, I can make a precise measurement because these little ticks in between, which this is obviously not to scale, can equal 0.1. And so if I have my meniscus falling above the line, I can say with some certainty, hey, it's at least 18. However, it's a little above 18. And so my uncertainty follows in that decimal place because I can say, yes, it's 18, but I think it's 18.1, or I think it's 18.2. I can add that decimal because I can create the value because I can see to that digit, like that decimal, my 10th decimal. So after you determine what the lines represent, you need to read the device to 1 decimal place past the smallest division on the measuring device. And so the smallest would be my 8 and my 18, so then I can make my decimal and to get my estimated value. However, if I'm working with a beaker and it's increasing to go up to 100, there's a lot more uncertainty in that, and so I can't exactly measure on a decimal point level. However, my uncertainty lies with my final digit that's in my 1 spot or my 10th spot, depending on how drastic of a change in measurement that is. So, significant figures, you're always going to have your tenths, your ones, your tenths, and your hundredths. And so when you're measuring, for example, right here, I can make, here's my 2, and I can say 2.1, 2.2, 2.3, 2.4, 2.5. but I can have those little tenths in between, so I can say, oh, it's 2.55, where your 5 here, my hundredth spot, is my uncertainty. But if I work with a ruler such as this, let me move myself up high, I have a greater width here where I can't tell you exactly, oh, it's 2.55. So I make my estimate where I can say it's above 2, it's below 3, it's kind of in the half. So I'm going to say 2.5, where my 10th spot is my now estimated digit. Thanks. Okay. So I want you to measure this line segment for me. Write it down, make your estimate, and then we'll talk about it here in a minute. So it's much like the ruler that we just looked at previously, where it's really hard to tell because I can say, oh, it's more than 3, but it's less than 3.5, and so I can say like 3.2. But if you measure with this ruler, you're able to make a more estimated value. And so take a moment to measure now. All right. So I can say 3.24. And the reason I can say that is I go, okay, here's 1, 2, and then I know it's less than my 0.3, but where does it fall for that for me? So I would say 3.24, where 4 is my estimated value, because I can say with certainty, I know it's 3, I know it's 0.2, I don't know what's here, there's my uncertainty. There's my estimated digit. So an example now is how much liquid is in each container. So I have a beaker and I have a graduated cylinder. And make sure to include your uncertainty. So when I look at the beaker, it's hard to tell decimal places because it's going by 10, but I don't have an indication of how it's moving up. And so when I make this guess, I can say 48, where 8 is my estimated value in my 1 spot, because I can say with certainty it's 4, but I can't say with certainty it's 48, the 8 part. When I look at my volume on my graduated cylinder, I'm always going to look at the meniscus to measure. And when I look at this, I can say, okay, it's increasing by 1. So I have my 10 imaginary ticks in here. However, I do think, hey, it looks like it's right on 24. But I need to give an estimated digit no matter what. And so even if it's exactly on there, for example, I say 24, I need to give a 0.0 because it could be under, it could be below that line. I am not certain. So I can say, yeah, it's at least 24, but I think it's 24.0. I think it's on the line because someone else can look at it and say, oh, I think it's 24.1. So your homework now is you need to complete the graphing worksheet and a metric conversion practice worksheet and turn those into Canvas when done. When you're in class, we're going to be working on a lab, going over volume, and so we will review some of these concepts. However, you should have enough to successfully complete the following worksheets. Remember, if you have any questions, please email me. But we're kind of fortunate. A lot of this is review, so it shouldn't be too bad. But anyways, have a wonderful day, and yeah, just email me if you have any questions. Bye.